Lesson 4.4, Angular Momentum. So linear momentum was P equals mv. But when we talk about angular and rotation, remember instead of mass for torques, they used moment of inertia. So moment of inertia takes the place of mass for angular formula. So angular momentum is going to be L equals I omega. Angular momentum is the L, I is the moment of inertia, and of course the omega is the angular velocity. The unit is going to be a kilogram meter squared per second, and our angular velocity must be in radians per second. When you rotate something, you exert a torque. More torque means a faster change in angular momentum. So our net torque is our change in angular momentum over time. Or if you'd like, torque times T equals our change in angular momentum. Just like linear, force was the change in momentum over time, or the impulse was our change in momentum. Same idea. Linear momentum of a system is conserved if the net force, external forces, are zero. Angular momentum of a system is also conserved if the net torque on the system is zero. A 10 kilogram solid disk with radius of 0.4 meters is spinning at 8 radians per second. A 9 kilogram solid disk with a radius of 0.3 meters is dropped onto the first disk. The second disk was initially not rotating. What is the angular velocity after the disks are together? So there's the bigger one, and there's the smaller one, and it falls down and lands on it. So we're going to need to know our moment of inertia. For a disk, our moment of inertia is mr squared over 2. So for the smaller disk, the mass is 9 kilograms, and the radius is 0.3 meters. Okay, so for our smaller disk, our moment of inertia is 0.405 kilogram meter squared. For the bigger disk, the mass is 10 kilograms, and its radius is 0.4 meters. So its moment of inertia is 0.8 kilogram meters squared. Okay. So now that we have our moments of inertia, we can say that our angular momentum is constant. Remember, angular momentum is the moment of inertia times the angular velocity. So I could say our first disk plus our second disk equals the first disk plus the second disk, just like we do with linear momentum. First, second, first, second. So we have 0.405 times the angular velocity of the, okay, that was the smaller one, the 9 kilogram, which was not initially rotating. The 10 kilogram disk, its moment of inertia was 0.8. And it was initially rotating at 8 radians per second. Afterwards, we don't know. But they do have the same final angular velocity. So I can just set it up so that they have the same final angular velocity. Call it omega f. So I have 6.4 kilogram meter squared per second equals 1.205 kilogram meter squared omega f. So omega f is the division of that, which is 5.31 radians per second. So it has slowed down from 8 radians per second to 5.31 radians per second. What is the torque applied if that takes 0.1 seconds? All right, so our torque is our change in momentum over time. Well, our change in momentum of the little, let's use the 9 kilogram one, the small one, its final momentum minus the initial over our time. So that is the 0.405. And its final speed was 5.31 radians per second. Its initial was not rotating, so its initial is 0. And the time was 0.01 seconds. And so it comes out to be 215, so it's 215 Newton meters. Angular momentum is conserved if the net external torque is 0. Linear momentum is conserved if the net external force is 0. And kinetic energy is conserved if the elastic collision. All right, let's talk about the direction of the angular quantities. We'll use the right-hand rule. So we're using our right hand. We hold our hand out with our thumb along the axis, and you curl your fingers in the direction of the motion. You may have to turn your hand upside down. So up here, it's rotating, so the fingers are there, your thumb's going up. Therefore, that angular velocity is pointing up. Whereas on the second one, in order to get your fingers to curl that way around, your thumb has to go down, and so that angular velocity is down. The vector is in the direction of the thumb. A person is holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. What will happen if he suddenly flips the bicycle wheel over so it is spinning in the opposite direction? All right, so if we look at the person on the turntable, the person, the wheel is the system. So the initial angular momentum we're going to call L, and it is going upwards. Afterwards, our final angular momentum must be L upwards. It has to stay the same. But if I flip the wheel upside down, the angular momentum is going to be negative L. So if I have L0 equals LF of the wheel plus LF of the person. Initially, here, let's put it this way. The initial momentum of the wheel is L, and the person is stationary. Afterwards, when I flip it upside down, assuming that the speed of the wheel stayed the same, it's now upside down. The direction is opposite, so it's negative L. So in order for this to be balanced, what do I need to add? I need to add 2 L's to have both sides be the same. So what's going to happen? The person is going to rotate with a momentum of 2L. So the person rotates in the direction the wheel was initially spinning with momentum 2L.